describing this. And first of all, in this, the very first thing that we should begin by describing is called a variable. A variable is the most important aspect of statistics. Your entire chapter 3, chapter 4 of when you go to DeVore is based out of variables. So we want to go ahead and understand what is a variable. Anything that varies. It's not fixed. Anything that is random. That's a variable. Let us go ahead and take some examples out here. So let's say that I want to talk about bicycle, right? And in this, I want to talk about the different aspects of a bicycle. And I begin with the first aspect, which is number of wheels. Now, the number of wheels that a bicycle has is 2. It's a bicycle. I just have 2 wheels in a cycle. So I'm going to go ahead and say that this is going to be 2. And because this does not vary from your cycle to my cycle, this is not a variable. Now let's go to the second example. So the brand of the cycle. The brand of the cycle can be different. It can be Hero, it can be Ladybird. I don't even know what the other brands are, but there can be many brands, A, B, C, D, etc. So the brand of the cycle will vary. So it is a variable. Yes, a variable. And because it is a categorical variable, it can be different names that can be attached to the brand of the cycle. We go ahead and call it as a nominal variable. A nominal variable is any variable which is categorical variable. Okay. Now, let's go to the third type. So let's say the next question is, what is the type of bicycle? Or, I will not write a type. I will say condition of bicycle. That's a better way of putting it out. So whether the condition of the bicycle is excellent, good, okay, or bad. This is also categories. I am giving 4 types of category: excellent, good, okay, and bad. So this is also varying, and hence it is a variable. But this is called an ordinal variable. What is an ordinal variable? Any variable in which ranking is possible. So for example, I know that excellent is better than good, is better than okay, is better than bad. It's like saying, give me the ranking of the students in the class. So I know the person who ranks first is better than second, is better than third, is better than fourth. If I'm able to give some kind of ranking in the categories, then it becomes an ordinal variable. Nominal and ordinal are both qualitative. But nominal has no categories attached to it. Ordinal has nominal has no ranking attached to it. Ordinal has ranking attached to it. This is, you can write this down, it is ranking involved. Right? Then you can, so we can make this actually variable, can be qualitative or it can be quantitative. Qualitative can be true, nominal, ordinal. It is the same as attributes, absolutely, yes. And quantitative can also be true. One is called discrete and the other is called continuous. A discrete variable is that variable which is a number, but it's not continuous. So I cannot go ahead and say 4.2, 4.5, 4.7. It will either be 4 or it will be 5. It's like saying how many, if I go from car, if I go towards car, let's say how many safety mirrors does the car have, or how many brakes does the car have, or how many, let's say anything which is discrete. So a discrete variable, or how many kids do you have, it cannot be in number, it cannot be in fractions. It has to be either 2 or 3 or 4. We can say that this cannot be in fraction, and you can write the example as number of kids. It should vary. Only then it is a variable. A continuous example can be the height of the individual. So it can be 4.4 foot 5 inch. It can be 5 foot 7 inch, 5.8, 5.9. It can be in fractions also. It can also be in intervals. Like for example, I can say that, the height of this person is between 160 to 162 centimeter. So I can give the continuous variable in interval also. So it can be 160 to 162 centimeter. But discrete, I cannot do that because it can only be some numbers without attaching the fraction to it. So it cannot be in fractions. Now, let's talk about how we can go ahead and summarize the data set. So write down summarizing data set. Very briefly, I'm explaining. This is never ever asked in any exam whatsoever. So the first is the tally frequency table. So for example, if I want to go ahead and want to make a table of how students go from their home to school, I can go ahead and say via foot, cycle, motorcycle, car, etc. And let's say that I want to go ahead and give some tallies. So in tally, what happens is you show 1, 2, 3, 4, and to show 5, you cut 4. So this is 5, 6, 7, 8, 9. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1, 2. So if I go ahead and give these in tallies, what I have shown here, then it is known as a tally frequency table. I'm giving the frequencies, how many people travel by what mode, but I'm giving these tally bars here. The second one is called a bar graph. So it's like this. If I go ahead and I make these frequencies, so for example, I say car, and I tell you that, 11 people traveled by car. And then I give you that, 8 people traveled by bike, etc. If I go ahead and I make these bars, each bar representative of the frequency, then it gives me a bar graph. These bar graphs can be drawn for both discrete and continuous data sets. So I can at any point of time say something like this. Students whose height is between say 150 to 155, there are these many students. Then between 155 to 160, I have these many students. Then 160 to 165 centimeter, I have these many students, and so on. So I can also have these continuous intervals, which tell me that for each interval, what is the frequency of the students. You would have seen this in your school life that, whenever we were making these bar graphs, and if we were not beginning from zero, we were beginning by a very high number, it's a tendency to show something like this in the beginning, just to tell that I am not beginning from zero, I am beginning from the center of some number line. So, anything below 150, anything below 150 is taken together. So I'm just going to draw something like this and then a line. And here you can say that this is the height student. Now, what we can also go ahead and do is take the center point of these heights of these bar graph and join them by a line. And if I go ahead and join them by line, something like this, suppose this is my next bar graph, then what I get is known as a line graph. So a line graph can be obtained by joining the center points of the bar graph. At last, you can also have a pie chart. So a pie chart is found by finding the proportions. For example, if I tell you that, I have 9 people here, 4 here, 11 here, and 2 here, I may want to go ahead and add them together. So 11 plus 9 is 20, 24, and 26. And now what I will go ahead and do is I will find the percentage. So I will say, okay, what is 9 by 26 into 100? I will get some percentage here. 4 by 26 into 100. 11 by 26 into 100. And 2 by 26 into 100. And once I find these percentages, I will say that my entire circle, it refers to 100%. So for example, if 11 by 26, it's approximately more than your, let's say, half of it, it's taking half of the entire thing, then very, very close to 50%, then what I will do is I will say, okay, maybe this entire thing, this is 11, whatever percentage you get, 11 by 26 into 100, 40%. This is what you will show by the motorcycle. So this will be a motorcycle. And then, 9 by 26 you will show here, and 2 by 26 will be very, very less. So this is a pie chart. A pie chart is always drawn by finding the percentages and then plotting that inside the circle, right? Now, let's talk about the frequency distribution tables. You may want to also go ahead and note that there are 2 kinds of frequency tables. One are called inclusive and the other are called exclusive. Both are continuous type of frequency tables. But in inclusive frequency table, both upper and lower limit is included. Whereas in exclusive frequency table, only the lower limit is included. Let me give you an example. An inclusive frequency table will look something like this. So if I take marks here and I take number of students here, so my marks can be 15 to 19, 20 to 24, 25 to 29, 30 to 34, and so on. So I'm including all students who scored 15 and all students who scored 19 and everything in between. And then I'm writing the number of students here. Something like this. Whereas when I talk about the exclusive frequency table, so I will have something like this. If I take marks here and number of students here, I can say 14.5 to 19.5 and 19.5 to 24.5 and so on. In this case, I will include students who have scored 14.5 in the first interval, but not students who have included 19.5. The students who have scored 19.5 will be included in this interval. So I am excluding the upper limit, and hence it is called the exclusive frequency table. This is called the inclusive frequency table. Now, just write down one formula that I want to define here. It is related to the number of classes suggested for frequency table. If someone asks you how many classes should I have, imagine a data set which contains data points from 0 to 1000. Now, one statistician may make intervals like this: 0 to 10, 10 to 20, till 990 to 1000. May give a class width of 10 and may make so many different classes. The other statistician may make classes like 100 to 200, 200 to 300 and so on, and just make 10, 11 classes. Question is, how many classes are optimum? What's the correct number of classes in frequency table? There are two different kind of rules that I've seen across books. The first one suggests between 5 to 15. This is the correct amount. Any number of classes between 5 to 15 is correct. The second suggests and gives a value. It says the number of intervals that you should have, which is k. It should be, sorry, not number of intervals, I should say classes. It should be 1 plus 3.322 log n to the base 10. So take an example. Suppose my n, which is the frequency, which is the number of observations that I have, is 1000. So I will go ahead and say 1 plus 3.322 log 1000 to the base 10. Now this part, it is asking me to what power should 10 be raised to get 1000. So 10 should be raised to the power 3 to get 1000. So this value will be 3 multiplied with 3.322 plus 1. So 3 into 3 is approximately 9. So I will just take this as 10 because this is 3.3. So I will take this as 10 plus 1. So it is 11. Which means if I have 1000 observations given to me, then I, on an average, can have 11 classes that I can divide my entire data set into. So this is the formula that is given in some books to find the right number of classes. How many classes should you introduce from your data set? Right. One last thing that I want to just kind of tell you before we end the class. This is related to what happens if the intervals are uneven. So for example, I'm doing some kind of comparison, some kind. I will, show you an example. But when I'm doing this comparison, the class size are varying. So one class size is 10 to 20, and the next class size is 20 to 45. And now I want to do some kind of analysis on this data set. If I want to work with this data set, her class size ke against I have some frequency. So if I want to work with this data set, I can go ahead and find something which is called frequency density. And this can be defined as value of frequency upon the width of the class. So for example, in this class, if I have, let's say, 4 people, and in this class, let's say I have 20 people. So the density will be 4 divided by the gap, which is 10. That's the width of the class. And the density would be 20 divided by the width of the class, that is 25. So this would be my density, frequency density, 0.4, and this is 4 by 5, so 0.8. Now you work with these. Now you can compare two separate classes. That, okay, 40% of the people are here and 80% are here, something like that. You can compare now after you are given, you have found everything in the densities. So if your classes have width which is not the same, then you can use frequency density for the purpose of comparison.